I'm going to present you the work we have been doing with Marceau and Dimitrios on the application of deep reinforcement learning for multiple access in the uplink, and especially for URLLC networks and IoT. So first, what do we need deep reinforcement learning? So in this workshop, we have seen many reasons, and the main reason is that standard protocols cannot meet the URLLC constraints. A few reasons are, for example, they cannot handle sporadic traffic patterns, so they miss a lot of transmission opportunities. They also struggle with strict latency requirements, so suffer from large delays. For example, the SOTIDA-LOA, like random access protocols, suffer from a lot of collisions when we increase the number of devices and the load in general. And they also suffer from interference with other users, which increases the error probability and decreases the reliability. So a few proposals, like a few new approaches have emerged to tackle URLLC. A few of them are NOMA that we saw in this workshop already, that increases the spectrum efficiency. There are also grant-free access that gets rid of like handshake procedures and allows devices to access the medium directly. And deep reinforcement learning protocols that have emerged in the recent years. And I know it's been a bit, people say it's a hot topic and it's a bit magical, but we're going to see in this talk that it's much more complicated than that. And most of the time, there are a lot of limitations, a lot of problems that are not mentioned. So a brief outline. So who doesn't know about deep reinforcement learning here? So everyone knows. Okay. So I'm going to do a quick recap of the global ideas and the main algorithms. Then I'm going to present the main applications of what has been done for uplink communications. And then I'm going to propose two solutions, two kind of algorithms we have developed, which are SARL and NOVA PPO. Using this for the time. So why do we say deep reinforcement learning compared to reinforcement learning? Is because we use deep neural networks. So deep neural networks are a family of function approximators with a large number of parameters that we usually denote theta. There are many kind of architectures that we can use depending on the type of data that we are studying. And on the left, I showed you a linear layer, we also called a feed-forward layer. And on the right, a recurrent layer. So the linear one is the most, like the simplest one, that just is a linear combination of the input and the weights that goes through an activation function, which is usually a ReLU, sigmoid, or any kind of non-linearity that you want to add to your model. And that's it. And you stack these linear layers to learn a complex function. For the recurrent neural network, this is usually used when you want to model sequences, like time series, sequences of words, or in our case, it would be sequence of state and actions. And the particularity is that the hidden layer is recursive. So you can see that here, hk is a function of hk minus 1. So you keep this hidden layer, that's this kind of memory, throughout your sequence. And you train deep neural networks with backpropagation and optimization algorithms like stochastic gradient descent or Adam algorithm. A few words on single agent reinforcement learning, because we're going to differentiate because using one agent or multiple agents. So the idea behind reinforcement learning is very simple. It's an agent, a decision maker that interacts with an environment. So it makes actions at every step and get an immediate reward for it. So the objective is to learn how to make the best actions, but contrary to multi-arm bandits, for example, we want to maximize the sum of future discounted rewards. So this is this expression. And this is modeled by a Markov decision process. There are two families of solutions. You have value-based solutions and policy-based solutions. In value-based solutions, what we want to do is to learn a Q function. Which is given in equation 2. And the Q function is, I mean, the intuition is simple, but it's much harder to compute in practice. The intuition is what you are in a state. You have a choice between different kind of actions. And every action gives you a value, but not the immediate value, which is a reward, but an expected future value. So you have a greedy policy, which is just you take the action that gives you the best Q function, Q value. So it's difficult to approximate in practice because you don't know the future. I mean, the future is stochastic. There are a lot of possible trajectories. So you can use the Bellman equation, for example, or deep neural network, which is deep Q networks, the most famous, I think, reinforcement learning algorithm. About policy-based solutions. So here it's a completely different approach where we want to directly maximize the sum of future expected reward, which is equation 1 here. So we want to maximize this. So we compute a gradient, which is equation 4. It's given by the policy gradient theorem. And we do gradient iterations with this gradient. It's not very easy. I mean, the main challenge with this gradient is that, okay, it's unbiased if we do Monte Carlo Monte Carlo sampling, but the variance of this gradient is very high because of the term R tau. Tau is a trajectory that you get with your current policy. So the main problem, as I said, is the variance of the gradient, mostly also because this term is optimized with respect to theta. Whereas you would like ideally to be maximized with respect to pi. And a small change in theta can make a big change in the policy pi, which makes the training very unstable. So there have been many methods to reduce the variance, like reinforce or actor critic methods. That's also quite famous. But the best approaches are the ones that are called trust region policy optimization. Maybe you know that, and this is what I'm going to present in more detail. So why am I focusing on this family of methods? It's because it has demonstrated the highest performance on the benchmark, which are Atari games. So maybe you know Breakout and Pong and all the different Ataris. And this algorithm is the best. So what is the idea? The idea is that when you want to do a gradient step, you don't want the new policy to be very far from the previous one. So you can control the variance of the gradient. So this is why in equation 6, you have a constraint on the KL divergence, that you don't want the new policy to be far from the old one.
What do you use for the first time?
So for the first term, it's what they call a surrogate objective. So it's very close to this term. The difference is that we don't want in the expectation to have your current policy because you want your previous policy, so you can do multiple gradient updates. So you do importance sampling, so you can rewrite the expectation, and you add the advantage function instead of the sum of expected reward, because when you put a baseline, in your gradient here, if you put R tau minus some baseline, it doesn't change the bias. It remains unbiased. And if you choose a smart baseline, it can reduce the variance. So, and they found that a good baseline is the value function, the state value function, which gives a value for a state you're in. And the advantage is just what the advantage of a function of an action, sorry, is how well is this action compared to the state you're in, compared to all other actions. So it's kind of a relative value function. So to estimate this baseline, we usually use a neural network. As often when we don't really know what to do, we use neural networks to approximate. And the problem with equation 5 and 6 is that the KL divergence is on the second order. So it's quite heavy to optimize. So there is a first order formulation for which gives the PPO algorithm, which is just the clipping of the objective. So equation 7. Now we move on to multi-agent reinforcement learning. So it's the same idea. You have agents that interact with the environment, except that now agents need to interact between each other. So what is more complicated is you can think of rock, paper, scissors game, for example. When I play rock, I mean, you can learn that I play rock, so you play paper. So, but then I learn that you play paper. So it's kind of, it's harder to find a best policy in this case. The framework is a framework from game theory, which is a partially observable stochastic game. So it's one of the most difficult frameworks to learn. So here we need to learn a Nash equilibrium because the game is partially observable. So we don't know what the others know. And we don't know their actions also. So we need to collaborate. We need to learn with the presence of other people. There is a simplification of this framework, which is a decentralized POMDP. And in this framework, which is much simpler and that we will use, agents are assumed to have the same reward. So it's simplified because it makes the game cooperative. Going to speed up a little, I think. And I'm going to present the different families of multi-agent approaches. The first one is the most intuitive one. When you want to model a problem with a multi-agent, you assume that the other agents don't exist. So independent learning, so equips each agent with a single agent reinforcement learning algorithm and consider the others as part of the environment. So you can use all kinds of different algorithms like IDQN or IPPO. But the problem with that is that when you consider that the others don't exist, the environment becomes non-stationary because when you learn, the other is also learning, so the environment changes. So you can be trapped in cases where your algorithm doesn't converge. So a lot of theoretical issues. But however, in practice, independent learning has demonstrated very high performance. A second approach to learn decentralized policies is centralized training with decentralized execution. So here the idea is that, like in real life, because where you could learn in a centralized way, for example, in a factory, you allow your agents to share all the information that they want to learn a policy. And when you deploy them to the real world, they are decentralized. So with this, there is no issue of non-stationarity during the training because agents can see everything. Nothing is hidden. And there have been a few algorithms like MADDPG for the policy gradient part, or the value decomposition network, or QMix for the value-based approaches. And finally, the last family of algorithm is the networked agents. Networked agents, it's a decentralized approach where you allow your agents to communicate with their neighbors. So it's an interesting framework, especially for IoT, I think, because there are some theoretical work on this, so very few still, but with strong assumptions. For example, the exponential decay property, which is a strong assumption because you assume that the effect of agents that are very far from you have no impact on your reward. But it's still interesting, especially if you want to increase observability. So what has been done on the application of DeepRL for uplink communications? First, from the MARL perspective, so the idea is just to equip every agent with a DeepRL algorithm. And most of the approaches, they apply the algorithms to their problem, and their contribution is on the problem formulation. So how they define the states, the actions, and the reward, not on the learning algorithm. Most of the approach, they use independent learning. So they assume that device is a DQN agent. And most of the time, they do not mention the theoretical guarantees and do not tackle partial observability. When they tackle partial observability, it's with a recurrent neural network. We're going to see that it's not the optimal. Then the centralized training and decentralized execution, they also are a few approaches with this. The problem is that it's not scalable because of the centralized training. So this is the issue. And for the networked agent frameworks, also some previous work. But here there is a big dependence on the network topology, as you can imagine, because it depends on the neighbors and it's hard to generalize because we would like to do like Monte Carlo and sample a lot of network topologies and average everything. But as it's very long to train reinforcement learning agents, this is in general not possible. So most of the previous works, they don't tackle non-stationarity and partial observability, and they do not tackle URLLC with strict deadlines, as we are going to do. Some centralized approaches, so centralized because there is only one agent. So here the base station is equipped with a reinforcement learning algorithm. One way to use centralized approaches is when to improve existing protocols, like grant-free access. There is this paper that dynamically adapt the parameters of sorted alloy, and this way they can use a better version of it. But still, this is still the same protocol. This is the protocol is still based on sorted alloy. So what we wanted to do in our previous work is to model the uplink problem as a partially observable scheduling problem. So if the problem is a scheduling problem, it's very, I mean, we know there is no collision. This is the main advantage. But the main problem is that we use a lot of communication resources to know if a device has a packet. So our idea was, what if we don't, what if there is partial observability, so we don't know who has a packet, so we try to guess. So if there is a packet, it's good, but if there is not a packet, we lost an attempt. So the conclusion for this this part is that the main problem is partial observability. This is what we're going to tackle next. So The first approach we propose is SecDQN. So it's a multi-agent approach, which is that every device is modeled by reinforcement learning agent. And if you remember, the main problem with independent learning is that everyone is learning at the same time. So there is a theoretical work that proposes decentralized training procedure where agents learn sequentially. So if I learn first and the other don't learn, that means that the environment is stationary. So in theory, it's supposed to converge. I'm supposed to converge to an optimal, and then it's your turn, and then the turn on someone else, and we do that like in a cycle. And they prove that this procedure of learning a best response converges in a special case of weekly acyclic games, which is the case in Markov games where the reward is collective. So the problem formulation. So for this work, we use a very simple approach to see how the algorithms perform. So we use one packet buffer where packets have the same times and can be transmitted in one slot. Packets have heterogeneous deadlines. We consider a periodic traffic model where users are heterogeneous and not synchronized. So we use a periodic traffic model here. So there is some traffic patterns to learn. And we use a collision channel model. We model a problem as a decentralized POMDP with these characteristics. So the state, so the local state of a user is its buffer. So how long has the packet been in the buffer? And the last channel, because we expect that when the last feedback that we have is a collision, that it will adapt dynamically to its transmission protocol. So the action is to transmit or not, and the reward is the feedback from the base station. So whether a successful transmission, a collision, or nothing. So in this algorithm, as I said, there are different agents that update their queue function sequentially on different what we call exploration phase. So in one exploration phase, only one agent learns. So we expect to be so the environment is stationary and it converges. To tackle partial observability, what is usually done is to use a recurrent neural network. So this is what we do here. And we start training the devices with the lowest deadline first. So we expect the most stringent devices to find their allocation protocol first. So they have more chance to be optimal. And the devices that have not been trained do not transmit at first. So we reduce the stationarity this way. We observed three main advantages. So we learn a better optimum than independent learning and CTDE. The training is much faster, and it's easier to increase the number of devices because the training is decentralized. So here is just what I've just described. So devices that are trained sequentially. And for the simulation results, so I show on the three figures the evolution of the URLLC score, function of the number of devices. We define the URLLC score as the number of packets that have been successfully transmitted, divided that the number of packets that have been received. So we can see that our algorithm outperforms on the dense traffic, for example, but is very close to the others in the two others. It's because CTDE uses centralized training, so it's supposed to be optimal because they can see all the information during the training. And it has also the smallest variance due to the training procedure, as we start with devices with a small deadline, and then we increase. I'm going to speed up also. For the training, it's much faster. So the training is a bit different because here I show the evolution of the score functions on the number of gradient updates. It is not very common because it's usually the number of episodes, the number of data that we see. But here I show the number of gradient updates because devices are not trained at the same time. So it makes more sense to compare regarding to the number of gradient updates. So the conclusion is that to go very fast, it's I mean, we managed to learn something, but in periodic traffic. If we have, for example, Poisson arrivals and more complicated traffic, there is nothing much in the traffic patterns to be learned, and we need to improve observability. For example, allowing devices to communicate with their neighbors. Now I'm going to show the other approach, which is NOMA PPO. So in this approach, we take the base station as a reinforcement learning agent, and it can schedule as many devices as it wants. Because the main issue with the centralized approach is that it doesn't know when a device has a packet. Even if it can estimate the probability of someone having a packet, it doesn't know. So it's hard to be URLLC. But what if it can select multiple users? Because if some users have a probability, I just pull everyone. So when we do that, we introduce collisions. So it's a problem. But we equip it with NOMA, so it can decode multiple devices at the same time with SIG. So another thing that we wanted to add is that some of the environment dynamics can be known to the agent. For example, the buffer incrementation. We know that when there is a time slot that when we go through time, the deadline of the packets decreases. And for this, there are two limitations on the traditional algorithms. That is the combinatorial action space, because when we can select multiple devices, then the action space is 2 power the number of devices, which is huge, and partial observability. Okay, it's a kind of the same traffic model as before. I mean, it's packets with heterogeneous 3 deadlines, collision channel, and the only difference is that we use NOMA, so we can decode up to B packets. And we consider here the aperiodic traffic, which was not considered before. When a device transmits, it also transmits its buffer information. And when a user is active but its transmission fails, it also provides information that it has a packet, which is useful. I'm not going to go in a lot of details, but just the state is all the buffers, all the channels of the users, and the observation, which is what happened in the previous slot. So we can see who was active, who has been decoded, what we observed, the buffer we observed, and the channel we observed. The action is a subset, I mean, it's a vector of 0 and 1, whether the device is active or not. And the reward is the sum of decoded packets. We define the agent state because solving a POMDP is hard. It's usually done by estimating a belief state. But estimating a belief state, we need to assume the dynamics are known, for example. And the belief state increases with the dimension, with time. So here we propose what we call the agent state, which is defined as by this tuple. So BKA, so the buffer of the estimate buffer of the agent K So it follows the same dynamic of the buffer, and it is filled when the base station calls a device. There is H shade, which is the last non-channel realization of the active devices. And we keep track of the last time that we polled a device, that a device was active, and when a device successfully transmitted. The property of this is that we show that it's a sufficient statistic for the action observation history. And proving that allows us also to form a new MDP with the agent state. That is very convenient because when we have an MDP, we can apply traditional reinforcement learning algorithms. So this was a summary of everything. The algorithm contributions to handle the combinatorial policy. We use a k-dimensional action. So instead of an output of one output, we output k values, and we use a Bayesian policy also to incorporate prior knowledge on the system. Because when we have the buffer estimates, when we know that we are sure that some agents, some devices have a packet, we know that a policy that is close to the optimal is the earliest deadline first algorithm. So we use this prior, and we also use this prior to encourage exploration. So when a device hasn't been polled for more than delta slot, delta being the deadline, it is polled. And we use the Bayesian policy like this. So this is the algorithm. Quickly to go through the results to conclude. Also, here I show the training of the algorithm. So the version of the URLLC score here function of the episode with different baselines, which are traditional reinforcement learning baseline. So the learning algorithm. So you can see that our algorithm, which is in red, converges much faster than the others and to a better optimum. And it has also the smallest variance. And regarding the performance, so here I did so essay nomastic is a baseline we took from a paper that is CTDE with NOMA, improved with NOMA. The random schedulers schedules devices at random, so it's like a lower bound. And we have also ID or QN with NOMA also, which is the distributed version, so the Grand Prix version with reinforcement learning. And what is interesting is that the multi-agent algorithm fails when at 30 devices, like the training is much less stable and doesn't converge. It is even less, it's even worse than the Grand Prix approach. And PDQ, I didn't mention, but it's the combinatorial version of DQN for large action space. So even this algorithm doesn't manage to handle 30 devices. And on the right, I show the James index of the URLLC score. So here also, our algorithm is fair. So the ablation study just to show the effect of the prior, but it's not necessary. And yes, to conclude, so we managed to model the problem as partially observable. So first we solve it in a theoretical point of view to transform it to an MDP using the agent state. And then we improve the PPO algorithm to handle the combinatorial action space and prior information. Thank you.